This is one of the largest and most ambitious engineering projects in the world, a massive hydroelectric dam that generates more kilowatts than almost any other on the planet. This engineering marvel produces so much energy that it can supply electricity to millions of homes. But how is electricity actually generated inside a hydroelectric power plant? In this video, we are going to discover how the Itaipu hydroelectric power plant works. Let's find out. Generating cheap, clean, and low-polluting energy has been one of humanity's greatest challenges for decades. But in 1984, one of the largest and most ambitious engineering projects in the history of the Americas began operating. The Itaipu hydroelectric power plant. Built on the Parana River, on the border between Brazil and Paraguay, this gigantic dam is capable of transforming the force of water into electricity for millions of people. To build it, engineers had to divert the course of one of the most powerful rivers in South America. It required more than $20 billion and an enormous army of 40,000 workers to raise this colossal structure. The workers faced suffocating heat, torrential rains, massive rock explosions, and the constant risk of flooding. For 7 years, they worked almost without rest to complete a construction project so enormous that it could be seen from miles away. Itaipu is one of the most powerful hydroelectric plants in the world. With a length of about 4.8 miles, it is more than 2.5 times longer than the Golden Gate Bridge. Its height reaches 738 feet above sea level, similar to a building with more than 65 floors. It holds back a mass of water almost 400 times larger than the entire area of Central Park in New York. And all of that water contains an enormous amount of energy. When the gates open, millions of gallons of water fall at an incredible speed through huge conduits, moving gigantic turbines that transform the force of the river into electricity. The plant supplies almost 90% of the electricity consumed in Paraguay and around 15% of the electricity used in Brazil. It produces around 90,000 gigawatt hours of electricity per year, enough to power entire cities and millions of homes. To produce that same amount of energy using oil, it would be necessary to burn hundreds of thousands of barrels every single day. But finding the perfect location to build a dam of this size was not easy. To generate enormous amounts of electricity, the river had to meet several extremely difficult conditions. It needed to carry a gigantic volume of water throughout the entire year. It needed to pass through a narrow area where the flow could be contained. And it also needed a foundation of rock strong enough to support the colossal weight of millions of tons of concrete and water. The Parana River met all of those requirements. Stretching more than 2,500 miles, it is one of the most powerful rivers on the planet and the second largest river in South America after the Amazon. At a point known as Itaipu, the river passes through a deep natural gorge hidden beneath the water. There, geological inspections revealed something essential. Under the riverbed, there was a massive layer of extremely solid basalt rock, strong enough to support the weight of one of the largest dams ever built. For engineers, the site seemed almost perfect. But there was one enormous problem. Building the dam would flood a huge area of farmland and natural forest. Thousands of families would have to leave their homes, while vast areas would be covered by the future reservoir. And before construction of the dam itself could begin, there was an even greater challenge, temporarily stopping one of the most powerful rivers on the planet. The solution was to excavate an immense diversion channel through the rock beside the riverbank. Its purpose was to redirect the river's flow away from the construction zone, allowing the work to be carried out on dry ground. The amount of earth and rock removed was so enormous that it was more than 8 times greater than the material excavated during the construction of the Channel Tunnel beneath the English Channel, one of the most famous underground engineering projects in the world. In 1975, construction of the Itaipu hydroelectric power plant began. The first major challenge was not building the dam, but preparing the land. For 3 years, thousands of workers used explosives, excavators, and heavy machinery to cut through the rock and redirect the course of the Parana River. 3 years after excavation began, engineers were ready to permanently divert the river. To do this, they placed dynamite charges at the ends of the concrete channel and prepared a critical operation that would completely change the landscape. But before releasing the water, they had to build enormous temporary structures called cofferdams. These worked like giant barriers made of rock and earth, dumped directly into the river until the flow was blocked. Their purpose was to force the entire river through the artificial channel, leaving the area where the dam would be built completely dry. With the river under control, the most important phase began, raising the giant walls of the dam. Engineers designed it as a gravity dam. That means its own weight is the key to its stability. The structure is so massive that the water cannot move it. To achieve this, the dam had to weigh approximately 61 million tons. The rock beneath it had to be extremely strong, because any weakness could compromise the entire structure. To optimize materials and reduce risks, engineers adopted an innovative design: a hollow dam with internal buttresses. This architecture allows the pressure of the water to be redistributed toward the base, where the structure is strongest, while also reducing the amount of concrete required. Construction was divided into 18 massive concrete blocks, each one 4 times taller than the Statue of Liberty. Each block was poured using huge steel structures that held the concrete in place until it completely hardened. One of the greatest challenges was controlling the heat of the concrete during curing. In large volumes, cement produces a chemical reaction that generates very high internal temperatures. And in a climate where outside temperatures can easily exceed 104 degrees Fahrenheit, uneven cooling could create catastrophic cracks. To prevent this, engineers built 2 gigantic ice plants directly at the construction site. The concrete was mixed with chilled water and ice flakes, coming out of the mixers at only 39 degrees Fahrenheit. Thanks to this system, the structure was prevented from cracking as it hardened. In total, 12.3 million cubic meters of concrete were used, enough to build more than 200 stadiums the size of Maracanã. The steel used would have been enough to build hundreds of Eiffel Towers. When the walls were complete, the decisive moment arrived, closing the diversion channel and allowing the Parana River to return to its course. Water slowly began to flood the valley, forming a gigantic reservoir. It took approximately 14 days for the water to reach its final level, with a depth of about 328 feet. That immense volume of water, around 29 billion cubic meters, became the force that powers the plant. It is capable of generating around 14,000 megawatts of electricity, enough to supply power to more than 24 million people. But controlling that much energy also creates risk. If the water level rises above the top of the dam, the pressure could damage the structure. To prevent that, engineers designed a key safety system: the spillway. It works like a gigantic escape valve. When the reservoir level rises too high, the excess water is released in a controlled way, preventing flooding and protecting the integrity of the entire dam. The dam spillway system is an imposing visual spectacle. When the reservoir level gets too high and the spillway gates open, the force of the water rushing out is brutal. It creates a waterfall capable of discharging up to 17 million gallons of water per second. That is equivalent to a flow 22 times greater than the famous Niagara Falls. Meanwhile, inside the hydroelectric plant, a gigantic underground installation houses the enormous turbines and generators responsible for transforming the energy of water into electricity. Each unit reaches approximately 88 feet in height and weighs close to 6,600 tons. They are so colossal that special transportation systems had to be designed to move and install them inside the plant. At the heart of each turbine is the rotor, one of the most important pieces in the entire system. Its job is to spin powerful magnets inside copper coils, allowing electricity to be generated through electromagnetic induction. Although these rotors are more than 52 feet in diameter, they must be installed with extreme precision, with tolerances of less than 1/10 of a millimeter. Even the smallest error could affect the performance of the entire system. To decide how much energy the plant should produce at any given moment, the operations team works in constant coordination with the energy authorities of Brazil and Paraguay. Electricity cannot be stored in large quantities, so production must be adjusted in real time to match demand. When consumption rises in the cities, more generating units are activated. Water from the reservoir falls with enormous force through 20 conduits, each about 34 feet in diameter and 466 feet long. Each one can carry around 700 cubic meters of water per second, directing it straight toward the turbines. This hydraulic energy drives Francis-type turbines, which convert the force of the water into mechanical movement. That movement is then transmitted through vertical shafts to the generators, where it is finally transformed into electricity. The plant is capable of reaching a total output close to 14,000 megawatts, making it one of the largest producers of hydroelectric energy in the world. The electricity is initially generated at a voltage of approximately 18 kilovolts. From there, it is transported through high-power cables to substations, where transformers increase the voltage so it can be distributed through the electrical grid. By raising the voltage, the electricity can travel over long distances with far less energy loss. Then, as it approaches cities, industries, and homes, the voltage is gradually reduced again until it becomes safe and usable. And all of this begins with something simple but incredibly powerful: falling water. The Parana River pushes through the dam, spins turbines larger than houses, activates massive generators, and sends electricity across 2 countries. What looks like a concrete wall holding back a river is actually one of the most powerful energy machines ever built. A machine capable of turning the movement of nature into light, heat, industry, and life for millions of people. Give this video a like if you enjoyed it, and share it with someone who might find it interesting. And make sure to subscribe to this channel and turn on notifications to keep learning. See you next time!